Hi, everybody. Thank you for showing up, and thanks for the organizers for letting me speak here. This is my second year. If you know me, you know I speak barefoot. It's kind of nice. It's a gimmick. Makes me feel more comfortable. You can take your shoes off as well if you want. Just, do it well. I'm going to talk today about research that we did at Argus. It's the work of more than one person, and these are the people. This is Raziel. Raziel is the radio guy. He's actually on his way to Brazil now to give the same talk. We had colliding events. Shir was in charge of signals analysis. There was a lot of decoding and analysis and trying to understand what we see in radio signals. This is me in the back, and this, which we will meet later, is an IKEA clothes hanger. Why? We will see. So, who's familiar with TPMS? Who knows what TPMS is? Okay, not many people. TPMS, tire pressure measurement system, or monitoring system, is a little device that sits inside of the wheel. It has a little battery, and basically it just transmits the tire pressure to the vehicle. Many reasons to do that. Flat tire, you want to know about it. If you have a bad pressure, then it affects the way the vehicle behaves or your fuel consumption. And in some vehicles, you can auto-inflate, provided that you know you have a pressure problem. And this thing has... Okay. All right. So this has been extensively researched. We're not the first people to look at that. There have been talks about this in a number of conferences. People were researching that, analyzing the signal. The signal is not encrypted. This is the #1 problem with it. And many people reached the same conclusion that you can analyze it, you can decode it, you can spoof it. And basically, what everybody said was this is harmless. There's almost nothing you can do with it. You can maybe cause someone to pull over. If they're driving on the highway and all of a sudden they think they have a low pressure, they will maybe pull over, right? That can be a beginning scenario of maybe hijacking someone or robbing them or just taking their car, whatever. Or, as I mentioned before, if you have an automatically inflating tire, then you could cause extra inflation. That will also cause damage. But the general consensus says the potential for damage is very small. And we saw that and we said, this is it's a very strong saying to say this is useless. Because when you say it's useless, it's not dangerous, then people stop caring about that. They stop looking at that. And we thought, what if we can prove that it is not as unimportant as everyone thinks, right? And we got our inspiration from this. What if we could cause that sort of distraction to many people at the same time? I mean, if it's just one driver, and like we said before, you get this little light and maybe they pull over, it has no significance. But what if we could make it happen on a bigger scale? So we start with one car. You need to receive the signal. You need to be able to analyze and parse it. It has different fields of information. Different cars have different standards. Then you have to modify it. We want to change the tire pressure value to something that will cause the alert, right? This little sound and the little light bulb on the dashboard, and then we want to retransmit it. This is the scenario for one car. Now, let's try to scale it up. These are the fields that you usually have, okay? Every single tire has their own ID. So in order to be able to talk to a specific car, you need to know the specific tire ID that the car knows. Otherwise, it's not going to work. This is why you have to listen first. You can't just transmit stuff. So you get all the information you need. Now, if you try to scale it up, then obviously you need to be able to capture multiple vehicles, right? So you need to do highway traffic capture. And of course, this is a little pun because the traffic is both radio and vehicles, but you need to be able to do that and analyze and parse all of it in real time. And if you look at the entire scenario, the whole setup, then you start by positioning multiple receivers. Why? Because this TPMS signal doesn't transmit all the time. It can transmit anything between once every 15 seconds and once every 60 seconds. So if I want to receive the TPMS of this guy, I don't know when it's going to transmit. If I wait for him here and it just transmitted 10 seconds ago, it's only going to transmit 50 seconds down the road and I'm not going to be there. So we're going to spread a bunch of receivers, which means that over this little piece of road, let's say 2, 3, 4 kilometers, I will definitely at one point catch his car transmitting. Then you need to collect them all, analyze them, and then extract the information you need, specifically tire ID, and be able to replace. Aggregate and sync. Why? Because if you look at this little piece of road, every car transmitted at a different point, but when we transmit, we want it to happen to all the cars at the same time, all the cars that are in a certain area. So this is the challenge. And let's look at this. Who knows this bridge? Anybody from Denmark or Sweden here? Hello, Gabi. This is the bridge between Denmark and Sweden. So let's look at that. We take an RTL SDR. This device is receiving only, but it costs about $9. You can get it on eBay or anywhere else. And we position a bunch of them, let's say 8, over this piece of road. So any car coming from here and driving towards the tunnel, at some point, the TPMS will transmit because it takes more than a minute to cross through the bridge. And then I take another device. This little guy is called the Yardstick 1. It is made by someone who spoke here last year. And this device is also able to transmit. And very easily, it has a Python interface. You just send it a Python command with the parameters, about $100, maybe $130. And then we transmit everything here. So right before the vehicles enter the tunnel, we transmit the signal. Now imagine that you have 40 or 50 cars traveling at 100 kilometers an hour, and all of them get this little boop. 1, 2, maybe 3 of them will take their eyes off the road and look at the dashboard. And when this happens at 100 kilometers an hour in a tunnel, there could be consequences. Now, we're not saying there will definitely be, but this thing only needs to succeed once in order to cause real damage. So, status report. We're somewhere in the middle. On one hand, we have a success. On the other one, we have a lot of failure. And this is actually part of the talk. Many times when you go to security conferences and someone is standing on stage and telling you what they did, they give you the solution. They don't explain to you how they got to that solution. What did they try? What worked? What didn't work? It's a lot less teaching to get the textbook answer. But if someone tells you the process that they took, then you can learn from that on how to do better research, in which directions to look, how to approach problems. And we're going to be, or I am going to be sharing what we did. We chose to do that because we wanted a learning experience. As I mentioned in the beginning, this had been researched before. We could have just taken all the work and continue from there. We didn't want to do that. We wanted to learn stuff that we hadn't done before, and that meant that we reinvented the wheel, right? We went through stuff that other people had already gone through and posted the results, but we didn't know how they got there. People just posted code, and we didn't know, so we wanted to learn. And of course, the meaning is that it took us a lot longer than we had expected. To the extent that the first time that we applied this talk to a conference, we applied with the abstract and then started the research, and we actually didn't finish the research in time for that conference. So we showed up and said, well, we wanted to talk about, but we failed. And this is how we also got the idea to insert that into the presentation. But now we're a little bit better. What have we learned during the work? It's not easy to find the signal. The TPMS signal is on two bandwidths, 440 or 34 in Europe and 315 megahertz in the US, that are for public use. There are many, many devices that transmit in this range. For example, your car keys, right? The remote keyless entry, they transmit in that frequency. A lot of other devices, because you don't need to license anything that works in that frequency range. So one of our problems when we were listening to radio waves was to determine which signal was in fact the TPMS. Remember, we started from scratch, so we didn't know what pattern to look for. We said, okay, we look for something that is maybe cyclic or whatever. So there was a lot of signal, and in the beginning, we didn't know what it was. We were chasing a lot of dead ends, and that's important. We had one particular problem. This is Laziel, and this is my vehicle. And this is the Hack RF, and here's the Yardstick 1. We had such a hard time getting a good signal, so we said, okay, let's take the best parameters. We're going to take the computer and sit in front of the wheel. What more can you ask for, right? The transmitter is 1 meter away from the receiver, not even, okay? And we sat, this is the underground parking lot, okay? It's not a nice air-conditioned hole like here. We sat there for hours, and it didn't work. Sometimes we got a signal, sometimes we didn't get a signal. Sometimes we got a signal, but it wasn't TPMS. Sometimes we got a signal that we thought was TPMS, but didn't have the cyclic timing that we were expecting. And at some point, after wasting many hours, we said, okay, we got the point, we accept our failure, we're going to take the shortcut. The shortcut is to take the wheel off the car, and then take the tire off the rim, and then look at the transmitter itself, because on these devices, you have the FCC ID code. And the FCC ID website will give you most of the information that you need, the frequency range and the modulation used. And this is a very good source of information, which we didn't want to go to. We wanted to figure it out, but we failed. And then, after hours of sitting on the floor, we discovered that my car doesn't have a TPMS transmitter. Imagine our surprise. So yeah, that was a little bit embarrassing. Of course, we immediately knew we were going to talk about that. That's why we took the photo. And then we found someone in the company that did have a TPMS. And this is the device. And here we're finally getting a signal. This scenario actually helped us because one of the ways to cause the TPMS sensor to start transmitting more than once a minute is if it detects a significant change in the pressure. And imagine that when you take the tire off and then you put it back on and you have to inflate the tire, the sensor is like, whoo, something is going on, let's party. And then it starts transmitting. So that was the first time we got a clear signal in many bursts, and that was a very big step for us, right? So we started, reading the documents and determining the signal. And what we actually needed the whole time was to find it. You see, this is what it looks like. It's very similar to the ones that I've shown you before. It was hard to tell, but here you can see a clear modulation. If you have any experience with radio, you can see this is a clear modulation of bits, and this is what we were looking for. And these were the parameters. If you know anything about radio, these will mean something to you. They describe the signal, how it is modulated, what are the parameters. There are many parameters for modulating a signal, and you need to know them all if you want to be able to demodulate the signal. So this is the mystery, and once we had that, things started to work for us. This is GNU Radio Companion. It's an open source package. Razi is an expert on that, and it took him a very long time to build this very sophisticated graph that was supposed to do everything automatically. But even that didn't work at the first start, and he had to rewrite a lot of stuff. So like I said, we reinvented the wheel. It was a lot of work. Of course, now he's a much better expert. But at the end, this is an open source package. Each and every one of you can do exactly the same. Doesn't cost anything. And then came the analysis. Okay, we have plenty of bits. Let's see what to do with them. Here I just changed it to dashes and dots because when you look at zeros and one, they're the same size, so it's harder to notice. But when you do this, the symbols are not the same size. So this is actually easier on the eye. Now, who recognizes this? So this is the city of Manchester. There is Manchester coding here, and we kind of forgot about that. So that also took us some time. You can have Manchester encoding in two different ways. So we were stepping on all the landmines during the research until we finally managed to get everything right. And that helped us because Manchester encoding also lets you know when the packet starts and when it ends. Because as you can see, there are a lot of bits here, and you really need to know which part of it is relevant. We tried even recording the signal and replaying it, and to see if we can analyze it. As you can see, this is again Razi's work. You can see the clear signal, and you can see the bits being decoded, and that worked very well in the lab, right? It's a recorded real-world signal being transmitted to our receiver, sort of a lab bench, I guess you can call it, and it worked. However, when you go to the car and you start driving with the same setup, all of a sudden, it's not as good. It was a lot harder to get a signal. Razi was driving around the city, and it didn't work. This is the closed hanger, which we mentioned before. The reason we needed that is because we had a directional antenna, which is perfect for this sort of radio signal. It's designed for this frequency. It's designed to look straight forward and not in a wide beam. And the office that we work at Argus is right over the road. The road is literally down the building. So we said, okay, let's put the antenna on the closed hanger, looking down, and record some signals. And as you can see, or as you might be able to detect, we are not at ground level. We were actually on the 36th floor, and we discovered that that was too much for the signal, and the only way to actually get a good signal was to go sit by the highway. So this is me sitting next to the highway in the middle of the Tel Aviv summer, recording bits. Okay? Very easy, same device, same setup. I just had to sit close to the road. After that, we said, okay, let's try to do the whole thing. Let's get a signal, analyze it, extract the tire pressure, change the tire pressure, and transmit again. We built a lab setup. In the lab setup, everything works fine. Really, you can see the bits going out, you can check the modulation, but again, when you try it in real life, it doesn't work. The benefits of this lab setup was that it saved us a lot of time. Instead of sitting outside waiting for signals and then trying our stuff, we were able to use a recorded signal. What you can see here is a device transmitting the recorded signal directly into the yardstick one. Instead of connecting an antenna, we connected the receiver and the transmitter with a cable. So that helped a lot. And here came another problem. It was time to try the transmission. And this is, again, the parking lot, the clothes hanger and the antenna, and we just couldn't get it work. It worked in the lab. We went down to the parking lot with the same device, the same equipment. It did not work. And remember, there's not a lot of work here. It's a bunch of Python commands going to a device, and all the modulation, all the radio stuff is happening on the device. It's not even on the computer. And we tried my computer, which is a MacBook Air, and it just didn't work. And then we tried Raziel's computer, which is also a MacBook Air, and it did work. And everything else is the same. It's the same script, it's the same device, literally the same yardstick one. And this is voodoo. We don't have an explanation for that. If any of you guys have an explanation, we would love to hear. Nothing else worked other than me dropping my computer and using Raziel's computer, which is almost the same computer. In fact, it's a little older, so we don't know. So eventually, where do we stand? It was time to see. It was like that when we got here, don't worry. It was time to see how this is working. So remember, our objective is to transmit a spoofed signal that will cause the light to go on, okay? And this is what it looks like. This is Razi's vehicle, and this is me, and we tried to sync the videos, so let's see. What we tried to do, the vehicle is parked outside the frame here, and we wanted to see whether if the antenna, which is here, transmit the signal while the vehicle goes by, we can spoof the signal. That was from close range, but remember, we wanted to cause the same effect on a large highway. A large highway would have 4, 5, 6, depending on your country, lanes. Each one is maybe 2.5, 3 meters. So you want to get a bigger distance. So what we were going to do is, after clearing this range, we were going to go over there. So this is the lowest floor of the parking lot. It was important to us to do it in a relatively sterile environment. We didn't want to affect anybody else. We were doing some driving. We needed no one to be there, so this was the perfect solution. Let's try again. Yeah, it's not going to work. We're going to skip this one. So where we got, so let me spoil you, it works, right? The car drives, we spoof the signal, and it works. And actually, we got it to work up to 30 meters away with this little antenna, the directional antenna, without an amplifier. So imagine, this setup can cause the same effect in roughly, let's say, the size of this hall. Okay, so cars driving here and a car driving at the back, this will work on all of them, provided that we got all the information from before. Okay, this is challenging. So, what did we get? The ranges that we got were up to 30 meters, which covers a lot, as I mentioned. And then we started working on the setup. Now, the way to do the setup, remember I mentioned we wanted to position multiple receivers and connect them all to a central station that will later transmit. The way to do that, we wanted to go as simple as possible. We had already spent too much time and effort on reinventing the wheel, so we went with Raspberry Pis. The Raspberry Pi can easily support an internet connection and this really nice RTL SDR, the little dongle that I mentioned before that only receives and costs $8. So we built an open VPN setup where the main station is the server, and then each of the other receiving stations is a client. And when you use that with certificates, then this setup is completely scalable. All you have to do if you want to add another receiving station is just clone the Raspberry Pi and change the certificate, and now you can add another one. And once they all connect to the VPN server, then they're all in the same subnet, they can talk to each other, and they can talk to the main system. The main system will be receiving the information from all the Raspberry Pis, doing all the calculations, and this is where the hard part is, and to be honest, we're not there yet. We chose to stop the research, I'll talk about that in a minute, but then you have to do all the synchronizing. When we receive the signal, we have to add a timestamp to it, because remember, the signals will be received at different times, but the transmission must happen at one time for everybody. So, why did we choose to stop? The point, all right, yes. All right, so we talked about the distance, and we talked about the back-end setup. And now, what's next? There are challenges here. First of all, there are many different modulations. This particular TPMS that we were working on, as it turns out, transmits in two different modulations. One of them is when the vehicle is static, and one of them is when the vehicle is moving. So obviously, we didn't care about the modulation when the vehicle is static, but that just shows you the different TPMS sensors from different manufacturers will be using different modulations with different parameters. So it is a matter of scaling up, but this is just research. It will not be creating something that was not done before. But if you want to do this, if you want to create the setup that we mentioned, then yes, we will need to go through more TPMS sensors. And there are many of them. There are many manufacturers, and it's challenging, but this is what you have to do in order to create the scenario. And the last thing is that synchronization. It's not easy. We would have had to play with that, but we chose to stop. Why? Because our objective was not to actually carry out this attack. This could be dangerous. We wanted to show that it can be done. So once we did it for one vehicle, then scaling it up is not the big challenge, and there was an agenda here. Let's talk about mitigation. If I'm showing a problem, then it's my responsibility to offer solutions. Otherwise, I'm just giving bad people ideas. Of course, the trivial mitigation that you can expect is someone to tell you, let's encrypt the transmission, right? But here's a problem. This little device is really small, and it's using a coin cell battery. It doesn't have all the computing power needed to execute encryption, right? Also, what happens if you change the tire? So you have 4 and maybe a spare one, but what happens if you damage the rim? So you get a new one, and then what happens? Who is synchronizing? So this creates more problems than it actually solves. The second option is to switch the operating mode from listening to the wheel to polling. If the vehicle asks the wheel, what is your pressure, instead of waiting for the wheel to report, then in order for me to be able to spoof that signal, I would have to listen, wait for that question, and then respond either quicker or stronger than the wheel. So this will make this attack scenario a lot more difficult. Not undoable, but a lot more difficult. But this mitigation also has its problems. How often do you do that? You can't do that all the time because this device goes to sleep when it's not transmitting. If you ask it every 10 seconds, then you're going to shorten the battery life. If you ask it every minute, what happens if there was a problem in between two questions? I asked it here, and then 10 seconds later, I have a flat tire. Is it going to take me 50 seconds to find out? So this is not a good idea. And the last mitigation is something that can actually already be done and relatively easy. The vehicle has many different sensors already inside it. One of them is measuring the rotation speed of the wheel. Now, when you take a wheel and you take the air out of it, the speed at which the wheel is revolving will change. And vehicles know that. Okay, this is, for example, how the ABS works. When you brake and the ABS senses that the wheels are not turning at the same speed, then it knows that you're starting to skid, and then all sorts of things start happening, so anti-skid and also ABS. So the vehicle already knows that. So imagine if you get a low pressure signal, and then you correlate it with the rotational speed, and you see that the speed hasn't changed, then you know that it is not, it's a false signal. And this is easy. You can do this already with existing vehicles, no need for additional hardware. But of course, the most important mitigation is not even in the vehicle. It's, as always, in security, it's about the users, and basically you have to keep your eyes on the road. And this applies to all of us. Being distracted while driving is one of the most dangerous things that can happen, and this is what actually started this whole research. The idea that we can cause distraction to many drivers at the same time. Now, an important message. It's doable. Yes, it's difficult. It requires a number of conditions. Maybe you need a really busy highway with many lanes and maybe a tunnel, but it's doable. And as I mentioned before in the beginning, it only takes once. The way the world works is that if something really bad happens, and then someone comes and claims responsibility and says, unless you pay me $1 million, this will start happening every other day. There is nothing people will do except pay, because there's nothing you can do. People get scared. So it is a threat that needs to be considered. Another thing which is actually our agenda. Yes, everybody who looked at it said that it was not dangerous. But there's a saying in English where there's a will, there's a way. And in our case, when we, as hackers, as white hats, and of course, when black hats do that, when there's malice, there's a way. A bad guy will always find a way to make your system do something it wasn't supposed to do. And I think that any of you who do actual security research, you know that most of the problems that we find are because the people who created the product were not taking something into consideration. Because people want to be good people. They want to think everybody else is good. So if the values of a variable are between 1 and 100, why would anyone put 200 or 1,000? Why would they do that? That's the sort of question you get from people. So we wanted to show that even when everybody looks at something and it looks harmless, if you really want to cause damage with it, there might be a solution. Or as somebody else framed it, if there's a way to do anything, there will be malice, because this is how the world works. And this is the most important thing. Scale matters. What I personally do at Argus is threat analysis and risk assessment. This is hacking, but on the earlier stages, at the design stages. And this is the best opportunity to find all the problems and all the risk scenarios so they can later decide what to deal with, what to mitigate, and what not to mitigate. And this particular case shows you that if I do a threat analysis and risk assessment on a vehicle and I look at the TPMS, yes, the result will be this is a viable risk scenario, spoofing the TPMS signal, but the risk score will be very low. Because the worst you can do to a single vehicle if you spoof the TPMS signal is maybe make the driver pull over. Or, as we're starting to understand, distracting the driver can also have security implications. But that's it. It's one vehicle. But if I do the same thing at scale, if the same scenario happens to many vehicles at the same time, at the same place, then the risk score is no longer low. It is actually very high, because in my best case scenario as an attacker, I can actually cause a car crash at 100 kilometers an hour inside a tunnel. This could be very bad. So scale matters. Things that look harmless on a small scale could look very differently when you go up the scale. Another thing which is not said enough, failure is part of the work process. For me, it's easy to say, I'm Israeli. In our culture, we fail all the time. We embrace failure, we talk about failure, we share our failure. Of course, we like blaming others for their failure. It's more fun. Everybody does that. But you cannot succeed without failing. And in fact, the most dangerous people are the people who always succeed and never failed. Because everything has always worked for them, and the first time that they're going to encounter something really, really bad, they will be unable to deal with that. Like, look at the computer. That thing was giving me trouble all the time. And I don't care, because everything has already happened to me. I'm standing here on stage, being recorded, and my computer hangs. Okay, so what? Happened to me before, and I survived to tell, right? In other cultures, failure is not accepted as such. Now, I'm not trying to change the culture of other people, but I am trying to change the culture of the security industry, the researchers. People think that if they share their failure, it's a bad sign, which means that they're going to lose their job, people are not going to think highly of them professionally, but in fact, sharing your failure helps other people. And learning from other people's failure teaches you better. And in fact, in HackLU 2 years ago, Angie Albertini, which is an amazing researcher, the guy does things that other people dream about. He was giving a complete talk about failures in InfoSec and about imposter syndrome, because everybody has that. Everybody who's ever been on a stage, people that maybe you and I look at them and say, wow, he's the best in his field. Everybody makes mistakes, everybody fails, everybody has imposter syndrome. So it's okay. It's part of our culture. And we need to accept that, and this will make us and our fellow researchers better at what we do. Thank you. Questions? Is that the same question from last time? Okay, Gabi. Wait, do we have a microphone for the questions, or is he going to shout? We have a microphone.
No, we do, yeah.
All right. So you said that scaling it up is hard, but how do the manufacturers do it? Because when I go to a service to replace the wheel, what do? They pull the TPMS module out and install it in the new wheel? Is it compatible with the new wheel? Does every wheel that you buy have a TPMS module inside, like a brand new one? How do they manage like all of the different encodings and packets, formats, and...
Your car either has TPMS in its wheels or it doesn't. When you go to a shop, assuming it's a licensed shop and not somebody's backyard, then they have diagnostic equipment which they connect to the vehicle through the OBD2 connector. They talk to the receiver ECU and they can sync it with new receivers. And this is their responsibility. When you buy a new car and it has 4 or 5 tires, they're all already synced. It is almost the same with the key. Sometimes when I was playing around with SDR and I was doing replay attacks on the key, then I got the system out of sync and my key stopped working. So I went to the shop and they just connected to the port, told the car, forget all the keys you know, here are 2 new keys, and that's how it works. But this is done with special diagnostic equipment that most people don't have or can't make, and the car shop, they know how to do that. Other questions? Also, if you have any questions, I'll be around here today and tomorrow. Feel free, and remember, failing is an option. No problem. Thank you.
Okay, Inbar, thank you very, very much.